Okay, I'm doing problem number 31 from chapter 15. It basically says that we have a physical pendulum and you're rotating it about a point that's not its center of mass, which is the only way you can rotate it. So you have this point D, and so we'll start off by simply using the expression for the time period of a physical pendulum, which is 2 pi square root of I divided by mgd. In this case, since we're not rotating through the center of mass, for I, we'll be using the parallel axis theorem, which would give us 2 pi. Now, first we'll take the moment of inertia through the center of mass, and it tells us to call that ICM. So we'll simply keep it like that. But since we're rotating it at a point D away from the center of mass, we'll have to add the second term, md squared. And we'll be dividing this entire thing by mgd, as that's in the denominator over there. So that's basically part A. Part B says, show that the period has a minimum value when D satisfies md squared equals ICM. So whenever we're finding minimum and solving minimum and maximum problems, it's basically telling us to find where the derivative is equal to 0. So we'll take, first find dt over dd, which would be 2 pi. Now we'll take this entire square root to the denominator, so this is ICM plus md squared divided by mgd to the 1/2 power, so that 1/2 would become a 2 in the denominator, and that 1/2 would then turn to negative 1/2. So we write this down here. Now we'll have to apply chain rule. So we basically see this entire term, ICM plus md squared divided by mgd. So we'll approach this part by using quotient rule. So first, the derivative of the numerator, ICM is just a constant. For md squared, we get 2 md, and we multiply that whole expression times mgd, minus the derivative of the denominator. So the derivative of mgd would be mg, since these two are constants, and d's the variable that we're differentiating against. So minus mg, and then the top term as it is. And in the bottom, we just write this whole expression squared. So now if you look at this expression, we see that this has a square root, so this must always be positive, and this is a squared, so this part must also be positive. So what I'll do now is I'll call this entire part of the expression k. So we get k times 2m squared d squared g, just simplifying this by multiplying all these terms out. And this part would give us negative mg ICM minus m squared d squared g. Okay. Now what we need to do is set this expression in the right side of the equation to be 0. Since k is a constant, it can never be 0. So we can see that 2mg d squared g and m squared d squared g are like terms, so we'll combine those two to m squared d squared g, and we'll write this expression as it is, so minus mg ICM, and this entire thing is 0. We'll move this to the right hand side, so m squared d squared g is equal to mg ICM. 1 m would cancel with the squared over here, the g's would cancel, so we end up with seeing that ICM equals md squared. And this is what they ask us to show, that for which value of D would ICM take its minimum value?